Hi, so in the previous lecture, we summarized the structure and properties of solids by building this table. And I want to talk a little bit more about this and give you an example. So one thing that we had talked about was the network crystals, the covalent network crystals. I had given you as an example diamond, which is just a pure form of carbon, and those carbon atoms are bonded to each other in this very long, extended covalent network. I want to show you a picture of that, okay? So here's a picture of two different forms of carbon, diamond and graphite. And both of these are just carbon. And both of them have carbon atoms bonded to each other in a covalent network. So these are two different types of network crystals that carbon can form. But I want you to notice something. The properties vary depending on how the covalent network is arranged on the molecular level. So in diamond, you see all of these carbon atoms bonded to each other in this extended three-dimensional network. Graphite, by contrast, has layers. So here we have two-dimensional layers. We have flat layers of hexagonal rings of carbon that are kind of layered on top of each other. So when we compare diamond with graphite, diamond has a three-dimensional extended covalent network, whereas graphite has carbon atoms in these flat two-dimensional networks that are kind of layered on top of each other. Now, when you think about diamond, you think about one of the hardest substances there is, right? Because of this extended three-dimensional network, whereas graphite in your pencil, okay, your pencil lead is not made of lead, it is made out of graphite. That's a relatively soft solid, right? And the reason for that is you don't have a three-dimensional network. You have these flat networks, and you have them kind of layered on top of each other. You get this kind of flakiness to it. So network crystals can vary quite a lot depending on the arrangement of atoms, even for the same substance. Both of these are just carbon, but they're carbon in different forms. So the kind of question you'll be expected to answer with regard to the structure and properties of solid is something like this. Looking at these different formulas, different chemical formulas, can you predict what type of solid each of these substances is going to form? So I'll give you an example. Silicon, CH3, CH2, CH3, this is propane. Ruthenium, calcium bromide, arsenic trihydride, sodium hydroxide, and gold. So all of these different substances, just looking at what kind of particles they have, can we predict what kind of solid they're going to form? All right. You might want to pause here and see if you can do this using the table that we generated in the previous video. All right, so let's think about this. Silicon, that's a nonmetal atom all by itself. That, out of all of the things in the table, that's going to be a network crystal or a covalent network crystal. It's a non-metal atom all by itself, so that's a pretty good clue that the only thing it can form is a network crystal. It can't be an ionic solid. It's not a metal, so it can't be a metallic crystal. It's not a molecule, so it can't be a molecular solid. By process of elimination, it has to be a network crystal. Now, propane, CH3, CH2, CH3, that's obviously a molecule. This is going to be forming a molecular solid. So those molecules are going to be held together by, in this case, London dispersion forces because it's a nonpolar molecule. Okay, ruthenium, it's an atom all by itself, but it's a metal. So ruthenium would form a metallic crystal. Calcium bromide, clearly a salt. Cations and anions, we are forming an ionic solid in that case. Now, arsenic, you might need to look at the periodic table. Arsenic is a nonmetal. Hydrogen is also a nonmetal. So this arsenic trihydride here, notice the way I'm naming it. I'm naming it as a covalent compound. That is a molecule. So the best bet here is molecular solid for a molecule, unless I have some kind of special information that suggests it might be a network crystal. There's no reason to believe it's a network crystal. Sodium hydroxide, even though hydroxide is a polyatomic ion, it is still an ion. So we have a cation and an anion, and this is going to be an ionic solid as well. Okay. So anytime you have a salt, it's going to be an ionic solid. Finally, gold. Gold, like ruthenium, is a metal all by itself. Its solid is going to be a metallic crystal. Metallic crystal or metallic solid, they're synonymous. All right, so I hope this gives you a good idea of the kinds of questions you might have to address on the structure and properties of solids.